Okay. Yesterday's lesson we dealt with common logs. Common logs are log base what? 10. So if there's no base written down there, we know it's base 10. We also had a change of base formula. Real quickly, we have something in math called the letter E, and it's used a lot in banking. It's used a lot in radioactive decay or in carbon dating, okay, and it is a letter E. It's an irrational number, much like pi, and this is how they came up with that number, which is 2.7818. We never use that number itself. We always use a letter E. Just like pi, we never use 3.14 for pi. All right, you're not going to use that anymore. We're going to use the actual pi button in the calculator because we want to be as accurate as we can. Here's how they came up with it. They took this formula and what they did, and that's how all these formulas are derived anyway, is just sort of playing around with it. They took $1, so that's a 1 out there in place of P. And they said, well, if we compound that yearly at 100%, R becomes 1. Yearly, it's a number times compounded for 1 year. Okay? So T is just 1. So we just have the N as our exponent. Okay? And if it's compounded, and we got 1 plus, if it's compounded once a year, 1 over 1 is 1, 1 plus 1 is 1, 2 to the first power, and we get 2. Okay? And so, well, what happens if I compound semi-annually for a year, and I figure out what that is? And it comes out to be 2.1 something. Okay, or 2.2, whatever it comes out to be. And it said, okay, well, compounded quarterly for 1 year. Remember, T is 1, so 4 times 1. And then compounded monthly, and so on. And as they did this more and more and more, compounded daily, that becomes 365. Then they figured out hourly. Then they figured out, well, what happens if we compound every second? And we find that this number approaches this irrational number, 2.71857, whatever it is. And they called that, it's an irrational number, and they called that the letter E. And that's what we do if we're compounding continuously. Okay, so that's where this letter E is derived from. In carbon dating, in radioactive decay, for instance, if we dig up this fossil and we do some carbon dating, it is continuously starting to decay. It doesn't stop. It just continuously decays. All right. And that's where we get this letter E from. So I'm going to give you a couple of examples here. We're going to take $5,000 and we're going to invest it at, let's say, 5 3/4% for 8 years. All right? And let's do compounded monthly. So the total amount, I'm going to write out the formula, 1 plus R over N raised to the NT power. Okay? And so we're going to take 5,000, 1 plus 0.0575. All right, that's our rate, that's our percentage, over, and we're going to compound monthly. So that n will become 12. And we're going to do this for 8 years, so 12 times 8. And we go to our calculator. Figure that out. You get 5,000 parentheses 1 plus 0.0575 divided by 12 raised, and 12 times 8, so we're going to raise that to the 96th power. And that sort of makes sense, that answer. So after 8 years, we're going to have $7,911.67. So that's the value we'll have after 8 years under that scenario. That's compounded monthly. Okay. Continuous compounding. Can we expect a number higher than this or lower? Higher. Okay, obviously, we're compounding continuously. If we want to compound quarterly, is this number going to be higher or lower? Lower. By not that much. And we've seen that it hasn't been that much. And we have a formula for that. And our formula that we use for continuous compounding is P E raised to the RT power. Think of that per. Okay? So the total amount is going to be the principal times this letter E for continuous compounding raised to the RT power. So plugging in our numbers here, we have 5,000 E raised to the 0.0575 times 8. We're putting that in our calculator. Now, I want you to look, if you don't have a calculator in front of you, please get one. And if you look in the first column in your calculator, under the log button, the next button down is ln. And the second function of the ln is e. So that if you hit second ln, e will pop up with a caret. You guys see it? All right. And we're going to, and it brings up a parenthesis as well. You don't have to worry about adding a parenthesis there. So 0.0575 times 8. Continuous compounding, you're going to have $7,920.37. So you got about $9 more compounding continuously. You would think it would be a lot more. What makes the biggest difference, though, is we found out was our rate, that interest rate. Even 0.1% of interest of your rate makes a big difference. Okay? So compounding continuously. All right. So now, here's a problem we're going to have. I'm going to erase this first part over here because I'm going to need this space. I want to know under this scenario, how long will it take me to double my money? Okay. So we're going to use this formula, and that's if it's continuous compounding. Okay. A equals P e to the RT power. If I'm investing $5,000, E, which is built into the formula, raised to the 0.0575. I want to know how long I want to solve for T before this amount becomes what? 10,000. Okay? Divide both sides by 5,000. And what do we get? 2. equals e to the 0.0575 t. All right? Michael, what if I invested $20,000? Would it take the same amount of time to double? Yes, it would. If this is 20,000, what does this become then? 40,000 and 40, right. So 40,000 divided by 20 makes us, that's still 2, right? If you want to triple your money, what does this 2 become? A 3. But the right side still stays the same, e raised to the 0.0575t.
Is that the final answer?
No, we want to find out how long before we double our money. What is t? And how do we solve for exponents? Use logarithms. Okay? So we're going to take this final line here, and we're going to write that. That is in exponential notation. We are going to write it in logarithmic notation. Log, what's the base? E. Log base e of what? 2 equals the exponent 0.0575 t. If you don't understand what I've done so far, let's raise your hand and let's clear that up. All I've done was I've taken an equation written in exponential notation and I've written it in logarithmic notation. But now I've got this log base e. All right. Well, let's define that. Log base e. What is it? It is ln. Log base e is ln. And we call this a natural logarithm. We have common log, which is base 10, but then we have a natural log, which is base e. So whenever we have log base e, we're going to write ln so that we can use our calculator. Okay? So take the problem we just did that says log base e of 2. Well, I'm going to write, instead of log base e, I'm going to write ln. You get that, Mike? ln 2 equals 0.0575 t. And then I simply divide both sides by 0.0575. So here's what we do in our calculator. We hit our ln button. ln 2, close the parenthesis, divided by 0.0575. And that gives us the number of years before our investment doubles, which is about 12 years. Okay, does that make sense? Solving for the exponent, we need to use logarithms. But if you have log base e, it is ln. Log base e is a natural log. You okay with that? Any questions? All right. Some of you guys have dealt with carbon dating in your biology class, AP Bio maybe, or chemistry, physics, I don't know. Some of you guys have already had some experience with logarithms in your science classes. In the book, they give you this formula. It's not a formula you have to memorize, because I will put it on the test if well, when we have a question like this. And let's see if we can work this formula. N of t. That just means something in terms of time, that's all. Don't let that parenthesis bother you too much. Is equal to n sub 0. That's what we start with. E raised to the negative k t power. And this has to do with exponential decay. Right? So, they give this example in the book where they found this scroll. And they're saying that this scroll was about 2,000 years old. They say that the scroll actually came from the time of Jesus as he was walking the earth. And they found out that they did a carbon-14 test on it. Carbon-14, I don't know how they do the test. But they found out that there was 78% of the original carbon-14 left. How old is that? They do this all the time. Well, for carbon-14, it sounds complicated, but it's really not. Carbon-14, the equation is n of t equals n sub 0 e. The k is 0.00012. That's the rate at which carbon-14 decays, times the number of years. Okay? What's left after a certain amount of years is 78% of the original. N sub 0 is the original, equals n sub 0 e to the negative 0.00012 g. We're looking for how old this document is. Somebody found it and claimed that it was from the time of Jesus when he was walking the earth. Okay, let's see how accurate this is. If you divide both sides by n sub 0, you get 0.78. So really, we may be able to skip this step doing a lot of problems like this. But if I divide both sides by the n sub 0, they'll cancel out. Okay, you see it? 0.78 equals e to the negative 0.00012 t. We want to solve for t. So we're going to use logarithms. Log base e, which is ln of 0.78 equals negative 0.00012 t. Divide both sides by negative 0.00012. So in your calculator, just hit ln 0.78, close your parenthesis, divide it by negative 0.00012. And they found that this document was about 2,070 years old. Okay. So that's how you would use these equations. Do we have any questions on this? You're going to find that in these next 2 or 3 sections, we're going to be doing more and more story problems. Now that we've learned all the properties of logarithms, natural logs, okay, now we're going to start doing some more story problems. So your homework then for today. Page 397, 399, 12 through 57 thirds, and I've got one more thing to show you. And then 72 to 79 all. One more quick thing to tell you. 35 to the x power equals 30. We did this yesterday. Change it to logarithm, log base 35 of 30, and that's what x equals. And how do you figure this out? Somebody tell me quickly. Right, use a change of base formula. Log of 30 over log of 35 for change of base formula. And what I said to you yesterday was that we can use any base at all to get the same answer. So log of 30 divided by log of 35, even if I use base E, ln 30 over ln 35, I will get the same exact answer. Okay? One of the sections on your homework says use natural logs in the change of base formula. So they want you to see that you can use ln as well as using regular logs. Okay? All right, so let's take a break and